Now that we have described the three different types of offshore wind turbine platform designs, we would now like to provide an educated recommendation as to which design is the best choice. In order to do this, we have isolated three main categories that can accurately model how effective the designs are. The three categories are CLIC, assembly and installation, CLIC, the financial cost of the platform design, and finally, CLIC, the overall stability of the platform out at sea. So first, we take a look at the assembly and installation processes for each platform design, and in this case, CLIC, assembly and installation was easiest for the semi-submersible design. In terms of assembly, it's pretty even across the board. Every platform design is assembled on shore using the modern technology present there, so in this category, the differences in structure between the three designs result in a negligible difference. The first large difference arises when looking at how the platforms are installed to their actual operating point. The semi-submersible design has a distinct advantage in the fact that it can be transported vertically. The semi-submersible design is independently stable, and because of this can be towed upright through the water to its point of operation. The other two designs must be towed horizontally and then erected offshore. The process of orienting the turbine vertically inserts another component of complexity and sometimes can result in damage to the turbine. The lack of this process is what makes the semi-submersible design superior in this category. Also, as a side note, the spar buoy design has a slightly better method of vertical orientation by filling the ballast tanks it uses partially to create a righting moment, which in turn allows the turbine to be erected with less force, making it second in this category. The next category we looked at was dealing with financial costs, specifically maintenance. In this category, CLIC, the tension leg design, and the semi-submersible design are the cheapest to maintain. The reason that the semi-submersible design is cheap is due to the fact that CLIC, it is so easily transported to and from port where it can be fixed. So even though the semi-submersible design is not as resilient as the other designs, the fact that it can be towed so easily makes up for this fact and increases its cost effectiveness. The tension leg design is also cheap in this regard because CLIC, it is resistant to the corrosive elements present at sea. The entirety of the tension leg design is underwater, which shields it from the heavy winds, rain, and ice that are present at the surface. The spar buoy and semi-submersible designs peek out of the surface, making them prone to all these corrosive effects. The other component of financial costs we analyzed was the obvious cost of materials. In this regard, we concluded that CLIC, the cost of materials depended on the type of mooring system that the specific design uses. The main difference between the three designs is that CLIC, the semi-submersible and spar buoy designs utilize catenary mooring lines to anchor them, whereas CLIC, the TLP designed mooring lines, go straight to the ocean floor. The semi-submersible and spar buoy designs use catenary mooring line designs, which consist of mooring lines that have a great deal of slack in them. Because of this slack, it naturally means that the mooring lines are going to require more material to make them. The TLP's mooring system consists of mooring lines that are anchored straight below the platform to the ocean floor. This reduction in material significantly increases the cost effectiveness of the TLP design. It is also worth noting that the semi-submersible design requires the most money out of the three because of the fact that it needs a lot of materials to build the complicated structure associated with it. The final category that we analyzed was the overall stability of the platforms when faced by forces present at sea. We separated this category into two parts, translational stability and rotational stability. In terms of translational stability, we reached the conclusion that CLIC, mooring lines affect translational stability. The mooring systems of each system are, as described in the previous section, are the sole factor in determining translational stability. The catenary mooring line systems allow the turbine to be pushed by the winds within a certain radius or zone before the mooring lines become taut and begin restricting motion. This ability to be pushed results in a drop of power output because the energy being used to push the turbines through the water could be used to push the turbine blades, thus creating energy. The TLP's mooring system, however, allows for almost no translational movement due to the rigidness of its mooring lines. Conversely, this allows for all the energy coming from the wind to be converted into electricity. For this category, the TLP has a large advantage when compared to the semi-submersible and spar buoy designs. In regards to rotational stability, the mooring system also plays a large role. We realized that in terms of rotational stability, it was handled in two ways, CLIC, using restriction as opposed to correction. What this means basically is that the TLP platform design uses a rigid mooring line system to restrict motion in any direction. We discussed how the TLP system does not allow for much translational motion and allows for rotational motion even less. This system accomplishes this by having the mooring lines be rigid and not allow for any motion. This is complemented by the other two platforms, which use correcting forces to maintain vertical orientation. The spar buoy uses its ballast system to establish a righting moment, which is a rotational force that wants to return to vertical orientation. This is similar to the semi-submersible platform, which also uses a dynamic ballast system that creates a correcting force to maintain vertical orientation. The difference between these two methods arise when looking at energy production. Because the semi-submersible and spar buoy designs use correcting forces, they allow for some rotational motion. This energy that is used to push the turbine rotationally could be used to push the turbine blades to increase energy production. Because of this, the TLP does not face this energy loss due to its strategy of restricting all motion and is the clear victor in terms of stability. Click. We compiled all of our results and inputted them into this graph to make a final recommendation as to which turbine platform design was the best. As is evident from this graph, the TLP design was the greatest in most categories and thus was our recommendation for how offshore wind energy should proceed in regards to implementing deep-sea turbines. In the end, our nation faces an impending crisis that we need to be proactive with finding a solution. We have informed you about the many options we have to solve this problem, as well as why wind energy is the best one. Although it faces problems when moved offshore, we have researched and discovered 3 different effective platform designs that could solve those problems. While any 3 of these designs would be a good choice, we have analyzed the pros and cons of each and concluded that one was a cut above the rest. Thank you for listening to our presentation, and hopefully you have learned something today. Are there any questions?